Yes? Awesome. Thank you. So, where's the rest of my stuff? So, good morning. We're going to try to finish off chapter 9 today, is the idea. Stuff about energy and collisions. I have to figure out where my notes box is going to sit. Let's put it there. And what I wanted to start with, actually, is another one of these center of mass calculations. So why don't we try this one? It's a semicircle. Put that in there. So, we will, first step is define our axes. So let's do the same as we did last time. We'll put y up in the middle. We'll put x off like this. And then we need to find the center of mass. So we can do that x center of mass equals, who knows? 0? Okay, I was waiting for somebody to. And what's the argument? Why would you say 0? That's exactly correct. You people know your physics. That's really good. So it's bisymmetry. That's the argument. Okay, so now we have to find dm. Find a dm that is a rectangle, a small rectangle that we know that we can figure out the area of. That we can find the area. Okay. So what I think that I'll do is I'll choose this one. We'll call it this dy. That's the width of it. Or I guess height, and then the width we'll call w, like that. And the w will be some function of y as it goes up, and we'll use Pythagoras or something to do it. So it looks like this, dy by w. The area of this rectangle is dA is equal to dy times w. Okay, length times width. And then I'll also note, if you want to call this distance, I guess, x from here to here, then w equals 2 times x. And so we can say that dA is equal to 2x times dy. And then dm is going to be, close to the bottom, dA times this mass per area. It's always the same kind of steps. So you say that it's dA times mass divided by the area of half a circle, which is, I guess, pi r squared over 2. Okay, so you would say dm, oops, here's my pen, dm is equal to 2m over pi r squared times dA, and which is equal to 4, there's a 2 times the x, pi r squared times x dy. And now we can use a little right triangle where this is y, this is x, and this is r, the radius of that circle. And so x squared plus y squared equals r squared. So we can solve for x as a function of y. It's going to be the square root of r squared minus y squared. So unfortunately, this is not looking like it's going to be a polynomial, but it's okay, we'll use an integral table. So the whole reason we're doing all this is we're going to use equation 9.4, which is that the y of the center of mass is equal to 1 over the mass times the integral of y times dm. Okay, so this is going to be equal to 4, we'll pull out all the constants, m over m pi r squared times the integral from 0 to r, that's the limits of y, times y times the square root of r squared minus y squared dy. So I'll just now put from an integral table, which is something that I would certainly give you on a test if you needed this. We know that the integral of x times some constant squared minus x squared in the square root dx is equal to negative a third times, 1/3 times a squared minus x. Running out of paper here, to the 3/2. Okay, so YCM equal to, the m's canceled. I've got 4 over pi r squared times negative a third. Instead of a, we've got r squared minus y squared to the 3/2. And we're going to, limits are r and 0. So plugging in the r squared minus r squared is 0. So it's just 0. And then we're going to minus the minus, so it's going to be plus a third of r squared when we plug in 0 for y to the 3/2. And this 2 cancels this 2, and you end up with 4 over pi r squared times r squared over 3. And now I'm going to slowly drag this over here. Like that. Need another page. So it's just, y center of mass is equal to 4 over 3 pi times r. And if you put it in your calculator, I got 0.42 r. So it's almost in the middle, but it's a little bit below the center there, right around there. Okay. All right. What else do I have? So I'll post that up. I go on Facebook sometimes and see things that students post. So I thought I would show you a comic that I found on Facebook, and how funny you're going to find it. I think it's trying to compare here teaching philosophies at different universities. So, you know. And actually, I've even modified it a little bit because that wasn't exactly what it said in the final slide there, but I don't know if anyone saw it. But until you're ready, we won't push you. So, and this is kind of in a bit of a reaction to, I have had a lot of students mention that in Math 135, you're not doing integrals yet, and I do sympathize. But, section 9.1 does involve this kind of integral that's behind here. And I think that you are ready, even if you don't feel ready. And certainly, maybe not these schools, but if you're going to Harvard or MIT or Stanford or even Berkeley, they're not going to skip section 9.1 because you didn't do integrals yet. So I don't want to leave you guys behind. I want to bring you forward. I'm here. Your TAs are here to help you. There's a TA in the drop-in center all morning. He's been there. There's these Vic College tutors. They're there. We're here to help you. And it is in, if you look ahead a bit in your Math 135 book, you'll see it. A couple more things. I thought I might actually show some of the results from this morning's pre-class quiz, just so you kind of have it. In a perfectly elastic collision between two perfectly rigid objects, the momentum and the kinetic energy are conserved. That's what elastic means. And if it's a perfectly inelastic, it looks like this. And can I actually switch to the video right now to show you the basic difference? Move the basketball out of the way. But here's this same track that you guys have in your practicals. And what you're going to be doing is setting up a force sensor and colliding the cart against the force sensor. And we'll talk more about that later. But you can show an elastic collision, which I think is like this. Yeah. Oops. So in an elastic collision, I think there's actually repelling magnets in these two things. So they go together, they bounce off each other. In a perfectly inelastic collision, what happens is they stick together by some Velcro or something. And there are lots of collisions that are between perfectly elastic or perfectly inelastic and elastic, but the basic idea is that some energy, kinetic energy, has been lost. And you can even see it. If you put them at the exact same speed and they collide, they almost stop. So certainly all that kinetic energy is not conserved during this collision. And then back to the doc cam, please. And then this one was about an explosion. A shell explodes into two fragments, one of which is heavier than the other. And the momentum change of the lighter fragment is exactly the same as the momentum change of the heavier fragment. So certainly the lighter fragment goes a lot faster, because it has smaller mass, but the same momentum. But that's the idea with collisions and explosions, is that the external forces are negligible compared to those internal forces. And so if there's only two fragments, they have to have equal and opposite momentum. That starts at rest. And then that was 1 point. And then 7 points, of course, are coming from, do you have any questions or comments about today's reading and or pre-class video? And if you leave that totally blank, you do lose the 7 points, as you probably noticed. But if you put no, then I assume that you understand it perfectly, so that's fine with me. But here's some questions, two questions that came up this morning. What's the difference between conservation of momentum and conservation of energy? And so these are quite different ideas, and they just come up in different situations. And one can be conserved or the other, or both, only in elastic collisions. But basic idea, conservation of energy, final equals initial, is when there is no work being done by some non-conservative outside forces. So if it's gravity, that's a conservative force, so it still conserves energy because you're using the potential energy from gravity. If it's a spring, we also, obeying Hooke's law, we also call that a conservative force because you use that potential energy of the spring, the 1/2 kx squared. But if it's something like friction or an applied force from somebody, then energy is not conserved, you're doing work. The other way that you can think of friction is that you're creating heat, and heat is getting radiated out into the universe, and that also does not conserve energy. Momentum is conserved when the net force is 0. And that's almost never true, except in collisions and explosions. And then what does the less than sign refer to? It just means much less than. And where it comes up sometimes in these arguments is that the external forces are much less than the internal forces, and therefore momentum is almost conserved. And we can see it, another way of looking at it is this thing I talked about at the end of last class, which is if the impulse is pretty close to 0, momentum is conserved. And another way of looking at it is that impulse is equal to the change in the momentum from before to after. And the work is equal to the change in the energy. Okay, so let's try this. I actually have 3 Learning Catalytics questions that are related to this. So this should be showing up on your phone soon. Okay, a basketball, and we can actually do the demo, starts by going down at an exactly 45-degree angle. And what I've given you is actually the components, the x and y components. They're both 5 meters per second. So it's, I don't know, square root of 25 meters per second that way, whoop, and it bounces. So what we're comparing is the change in the, I think what you're seeing is the x component of the ball's momentum just after compared to just before the collision with the ground. Think about that. You have to type in a number in kilograms meters per second. Think about it, figure out the number, maybe chat with your neighbor. So the change in the x component was just 0. Okay? Because it's going, the x component of the velocity was the same just before and just after the collision, according to my information there. So, see how that looks there? It's weird results, but anyway, let's just solve it. So this delta P is going to be the mass, 0.1, times the V final in the Y minus the V initial in the Y. So it's going to be 0.1 times 4 minus negative 5. So it's going to be 0.1 times 9, I think, right? So it's going to be plus 0.9 kilograms meters per second. Make sense? And actually, one more question. Let's put that just on. This one's a more conceptual question. We've talked about elastic versus inelastic. Do you remember what it is? Can you tell, I guess, is the question. I'll give you 1 minute to discuss, and then we'll move on. Timer done. Okay. Yeah, so this is actually not an elastic collision because the kinetic energy of the ball just before the collision is a little higher because its speed is a little higher. Its original speed is the square root of 5 squared plus 5 squared. Its final speed is the square root of 4 squared plus 5 squared. I don't know what that is, but it certainly slowed down a little bit, which means that for some reason it must have lost a little energy during the bounce. It probably did, right? Maybe it started spinning. But also there may have been some heat generated in the carpet or something like that. Okay. So I've got some more slides for you. Thinking more about what you're doing in practicals this week. This is impulse and the impulse momentum theorem. So impulse is an integral of force over time. So if you make a plot of force versus time and you look at the area between that curve and the zero, F equals 0 line, then that's the impulse. And it is a vector quantity, so if the force goes below, you got a negative area, I guess. Units are whatever this axis is times this axis, so it's newtons times seconds in SI units. And the impulse momentum theorem states that if you're doing this force acting on an object over some time, then the impulse equals the change in momentum of that object. And it's a vector equation, so really what that means is that there's two equations. The impulse, the component of the impulse in the x direction equals the change in the x momentum, and the component of the impulse in the y direction is the change in the y component of the momentum. And what it often looks like, and this is what you're doing actually in practicals, is that you've got something moving. So let's say you've got a ball, which is initially going in the positive x direction. Then it hits the wall and bounces off the wall. So it's a short little collision, and maybe it's the force sensor, so maybe you're sending your cart this way, there's a force sensor here, and boom, okay? And the force sensor, I believe, is set up so that you get positive is pulling and negative is pushing, so it goes negative. And actually, I guess if the x-axis is this way, your force is to the left. The force of the wall on the ball is to the left, so it's a negative force in the x direction. And this is the impulse. And this little time interval is the duration, I guess, of the collision. So while the ball is squished up against the wall, or while the magnets in your cart are repelling the magnets in this bumper, or while, I guess, that force sensor is bending. So something has to bend during the collision, and that's what gives you this delta t. And when contact begins, it reverses around and flips its momentum. And we'll do an example, I guess, which is similar to what you've been doing. Let's say you've got a 0.5 kilogram cart, rolls to the right at plus 1.2 meters per second, and then it collides with a force sensor. And you make the little plot of force versus time on your computer, and you find that the area is negative 1.0 newton seconds. What is the velocity of the cart immediately after the collision? So before, you've got this cart flying along like that. And P initial is equal to the mass times B initial, which is equal to 0.5 times 1.2. So it's half of 1.2, so it's equal to plus 0.6 kilograms meters per second. And then we've got the impulse momentum theorem, which is delta p x equals j x. Okay, and so this delta means the final, px final minus px initial is equal to j times x. And we can solve that out for the final. P final x is equal to p initial x plus your impulse. So it's going to be the plus 0.6 from here. It's your p initial. We can put little x's on here if you want. And then plus 0.1. I'll show you minus 1.0. Let's get it right. So 0.6 minus 1.0 is negative 0.4. So it does turn around. And we can, I guess, ask the question again, is this an elastic collision? And the answer is no, I guess, because it's lost. V final is equal to P final divided by M. I keep forgetting to put the little x subscripts, but let's do that. Negative 0.4 divided by 0.5 kilograms, and you get it's negative 0.8 meters per second. So its final speed is 0.8, and its initial speed was 1, so that's why I think it's inelastic. Okay, because the absolute value of V final x does not equal, well, it's actually not even, it's less than the absolute value of V initial x. So energy was lost. I don't know if it helps to, just a little bit better. Okay. So, impulse changes your momentum. And impulse has to do with the force that you feel multiplied times the time during which you feel that force. So this explains airbags. Let's say you get in a car accident and you're initially traveling at 50 kilometers per hour and you hit a tree which is traveling at 0 kilometers per hour. So you must now change your momentum. You have to change your speed from 50 down to 0. So you must change your momentum. Your mass times 50 is going to be the absolute value of the change in your momentum. And that's true, because this tree is fixed on the ground and you were going 50. So that's what's going to happen. You're going to stop. Question is, are you going to stop in a very short amount of time by flying forward and hitting the hard dashboard of your car? Or are you going to hit the big cushy airbag and stop over a longer duration of time? Same change in momentum, same impulse, but now you've got a different delta t. You have to go from mv to 0. If you hit the airbag squishes during impact, lengthening the time of the stop, and so the maximum force that you experience is less. Okay. The product of F times T is the same in both cases. If T is larger, then the force is less. And let's think about this one. Put this up on your phone. So I don't have this one, but we're going to do a thought experiment where you have two objects of the same mass, and you drop them from the same height, and they fall down and hit the ground, and then they do different things. The rubber ball bounces up. It's almost elastic, right? So it reverses its direction after the hit. The damp cloth, also 100 grams, just stops. It goes and just stays on the floor. So, do they receive the same impulse from the floor, or does the ball get a bigger impulse, or does the damp cloth get a bigger impulse? I'll give you a minute to think about that and click in. Okay, it stopped. So, answer is C. Now, this was a bit tricky. This is not necessarily about the duration of the time. I think I heard some reasoning that maybe the damp cloth Would it take a longer time to impact? Not really sure. But in fact, I'm not asking you about the force of the floor on the object. I'm asking about the total impulse. And the total impulse is simply the change in momentum. Those are equal. That is the impulse momentum theorem. Impulse is the change in momentum. They're kind of synonymous. So all you need to know is the change in momentum. If they both stopped, it would both have the same change in momentum. But the ball doesn't stop. It reverses. So you have to do your negative minus your positive. You end up with 2. Okay? If it flips, something flips its direction, then its change in momentum is 2 times its initial momentum, or negative 2 times. Make sense? And that's why it's twice as much impulse on the rubber ball as you get on the damp cloth. I tricked you. Okay. Next up, I'm going to do this elastic collisions math. My math is a little bit easier than Wolfson's math, though, and I'll show you why. So what's an elastic collision? Let's straighten this out. Any quick collision conserves momentum because the external forces are usually negligible during the collision compared to the collision forces themselves. Okay, so they all conserve momentum. But often in collisions, the kinetic energy after is a little less than the energy before because something changed. Usually some heat was created and lost to the environment. Or sometimes there's some damage. If the Hummer crashes into the Toyota, then the Toyota gets, all the metal in the Toyota gets all bent up and damaged. And that requires energy. Somebody has to fix that, and it takes energy to bend metal, deforming or heating the colliding objects. However, if the kinetic energy is conserved, then we say the collision is said to be elastic. And when you play pool, there's not very much damage and there's very little heat created when 2 billiard balls go click together. And so those are pretty close to elastic collisions. It's a good way to think of it. Something where nothing gets really deformed. So, there's a bunch of equations now. If we're doing things in one dimension, then there's 2 equations. There's conservation of energy, which is the 1/2 mv squared total of all the objects equals the 1/2 mv final squared. And then you're also doing the mv equals mv, and they're different because one of them's squared, one of them's not squared. So there's going to be a lot of equations, but the basic idea is that what I'm going to do is set the v2 initial equals 0. So that's my trick. And that simplifies our math a little bit. Okay. So that's the situation. These are the equations. Momentum conservation is m1 times v1 plus m2 v2. What I'm going to do is start with the ball at rest. And the idea here is that you can always, if it's not at rest, you can always switch to a reference frame using relative velocities in which ball 2 is at rest. So if you look in Wolfson, he's got a whole other giant term on his equation 9.15, but I never use that. This is the equation I would put in my 8 sheet. Just this one and this one. And just switch to a reference frame where ball 2 is at rest. It does take a couple pages of algebra to get that result, but it's not too bad. Okay, I've done that now. So now I'm going to do a demo. Let's do. I'm going to put the tennis ball on top of the basketball. I'm going to drop it. Ready? Just drop them both together if I can. I have to have a steady hand. Nice deflection. Good, okay, so what happened there? And so what we're going to do now, I don't know if you saw that coming, but we're going to analyze the hell out of it using math. Because that's how I roll. Ready? Of course you're ready. You're ready. You are ready. You're ready right now? Okay. I'm referring to that joke. Okay. First, what I want to do is think about this motion in terms of all these segments. So, it started with free fall. I released it from rest, it fell down. We can do it. You're ready. You can use conservation of energy as it falls down. Segment 2 is it's a bit hard to picture, but I'm going to imagine that there's a tiny little gap now between the tennis ball and the basketball, so that the first thing that happens is the basketball is going to have an elastic collision with the floor. And I'm not going to use the carpet, I'm going to use the wood floor, so that we're just going to simplify things by saying it's elastic collision. It's just going to reverse its momentum. Segment 3 is that then you have an elastic collision between an upward moving basketball and a downward moving tennis ball. And then segment 4 is what happens afterwards, and maybe how high does the tennis ball go before it hits these students in the front row. Okay? Let's do it. Segment 1. This is the free fall. Well, let's use height 0.82. Oh, I think I did more than that, but we've got here that 1/2 mv final squared is mgh. It goes down square root. So I put a plus or minus of this square root because I know it's going down. So v final equals plus or minus square root of 2 times 9.8 times 0.82. Because my calculator, there it is. So let's do square root of 2 times 9.8 times 0.2. So just before it hits the ground, I'm going to say it's going 4.0 n meters per second, and it's going to be down. You kind of know that, right? So even conservation of energy tells you the speed, and then your own mind tells you that the whole thing's going down, right? So it's the negative. And then segment 2 is the boing, when the basketball flips its direction. And now it's going plus 4 meters per second. Now here's the collision between the basketball and the tennis ball. We call that segment 3. A 0.5 kilogram basketball moving upwards at 4 meters per second strikes a 0.05 kilogram tennis ball moving downwards at 4 meters per second. Does that make sense? This is what's going to happen. First they're moving together with a tiny little gap, then boom, the basketball bounces, and then there's going to be a collision between what's happening is the basketball is now going up and the tennis ball is still going down. Okay? And we're going to use that equation 9.15 to find the final velocity of the tennis ball. That's our goal here. I think I'm going to label it, so we're going to call this one the 2, and this one the 1. The tennis ball is 2, and the basketball is 1. So we can do this like a homework problem. Okay, so we're going to say that M1 is the basketball, the 0.5 kilograms, and M2 is the tennis ball, the 0.05 kilograms. And from the ground reference frame, then you've got the before of the situation is going to be 2 is going down at 4.0, and 1 is going up at 4.0. Okay? This is V initial 2. And V initial 1. Okay? And then I'm going to switch to the reference frame in which the ball 2 is at rest. Because the equation that I like to use, I don't like to have the ball 2 have an initial velocity, in which tennis ball is at rest, And what I'm going to do there is I'm just going to add 4 to all velocities. And then what I have to remember to do is subtract 4 from all the velocities at the end of my thing to get back to the ground frame. And that saves me a whole lot of math. So now my before situation looks like this. The tennis ball is just sitting there. There's 2, v2 initial equals 0. And then the basketball now is coming up towards it at, what do you think? Exactly, 8 plus now 8 meters per second. So I guess this minus 4, add 4, get 0. The plus 4, you add 4, you get 8. So that's the relative velocity of these two balls now. And now we're going to use this equation, 15, I think, to find V2F, okay, in this frame. So V2F is equal to 2m1 over m1 plus m2 times V1 initial is 2 times 0.5 divided by 0.5 plus 0.05 times 8. And I got on my calculator plus 14.5 meters per second. Okay. And now don't forget to convert back to the lab frame, or the ground frame, by minusing off all you subtract 4. And so V2 final is equal to 10 plus 10.5 meters per second. Okay. And then segment 4 is just, I guess, I wanted to know how high the tennis ball goes before it comes back down and hits you all. That look okay? So segment 4 is that you've got a free fall of a tennis ball on the way up. It starts with the initial now is 10.5, and then you use conservation of energy, and GH plus, I guess final is that it stops when at the top of its height, and I ended up with 5.6. So you drop the balls, both the balls together from 0.82, and the tennis ball ends up 5.6 meters above, so that's why it flies up really high. And I have another fun toy. Where is it? Oh, there it is. Which Kevin brought. And you even have we have a cool video as well. Let's try it in real life. So now, okay, one tennis ball on top of one ball. Why not put 3 little balls on top of the bottom ball instead of maybe 3 times as fun? So now I've got, let's drop it from about here. And again, I have to have a really steady hand, which I don't. Ready? And I guess hopefully everybody on the floor is ready. I want to close your laptops with. The red ball is gone. Oh, there it is. I don't know if anybody saw that. It really went flying. I totally didn't see it. Maybe I should drop it from a lower height. Do you have the yellow one? Let's try it from a lower height and see if we can make it a little better. This is my last thing here, so let's try it. It's just too much. Did you guys see it? I couldn't see it at all. I guess I'm too close to it or something. Okay, can we go to the video? So Kevin did this in his office and made a video. So please show it. Boom. Okay, so the same sort of thing. You've got all this momentum that's in that bottom ball. It gets transferred to the upper ball. Upper ball has smaller mass, and so it picks up a huge velocity. This is actually the same thing that happens when a supernova collapses. So what a supernova is, type 2 supernova, is you've got a white dwarf, and it exceeds some mass, usually because it's got some companion adding to its mass, and then the electrons in the outer orbit of all the carbon can no longer support itself against gravitational collapse, so it starts collapsing. And it goes down and down and down and down and down, all of this material, until it hits a very solid sort of bottom, which is when the actual nuclei collide with each other. And you've got pure neutronium, where all the little nuclei are just pushed up against each other. That's an elastic collision, and what happens is the outer layers of that supernova now go flying off at huge, huge velocities, carrying all the momentum that the original collapse had, and that's why it blows away part of the whole galaxy. And, in fact, you guys have a break. I don't think you're going to see me until Monday, November the 13th. Don't forget to do your homework, chapters 8 and 9. That's going to be the first day you're back from break. It's going to be a homework assignment. There is a pre-class video. There is a hobbit door with a doorknob in the middle, which is not good. Why is it better to put the doorknob away from the hinge of a door? We're going to talk about torque. Have a great break. See you.